This is the lecture number 5 for the chapter matrices, and we are discussing the exercise 3.3, and I'm taking the question number 6. You have to prove that A transpose into A is equal to I, and the matrix A is given as cos alpha, sin alpha, minus sin alpha, cos alpha. So A transpose, you find the transpose of this matrix which will be cos sin alpha minus sin alpha cos alpha, and multiply these two, you'll get cos square alpha plus sin square alpha cos alpha sin alpha minus sin alpha cos alpha. You know how to multiply it, the two matrices. If you don't know how to multiply, first of all go to the previous lectures, see the multiplication of the matrices, do 4 5 question of multiplication, then you come to this exercise. So multiply these two matrices, cos square alpha plus sin square alpha cos alpha sin alpha minus sin alpha cos alpha. You are getting sin square cos square alpha is 1, sin alpha cos alpha minus sin alpha cos alpha 0. This is also 0 and this is equal to 1, then which is the identity matrix. Now in the remaining question of this exercise 3.3, and there's a matrix A is given, you have to prove that is a symmetric matrix. So I've just told you that you can simply tell only seeing the matrix whether it is symmetric or not. You see the diagonal element, whatever the matrix A is here, element is same, whatever element here same is here, whatever element same is here, same is here. So it is a symmetric matrix, but you have to prove it. To find the transpose of that matrix, so rows into column and column into rows, which is coming out to be same. So it is a symmetric matrix. Now you have to prove that this matrix is a skew symmetric matrix. Now the diagonal element is 0, these elements are of the opposite sign, these elements are of the opposite sign, these elements are of the opposite sign. So naturally it will be a skew symmetric matrix, but you have to prove it. To find the transpose of this matrix, 0 1 minus 1, 1 0 1 minus 1 0 1, 1 minus 1 0 1 minus 1 0. Take minus common in it, 0 1 minus 1 minus 1 0 1 1 minus 1 0, which is the matrix A. This is minus A matrix, which is a skew symmetric matrix. So this is the way you can prove that it's a symmetric or skew symmetric. Whenever you have to prove that a certain matrix is a symmetric, you let it P, and whenever you have to prove that a skew symmetric, you let it Q. Otherwise you can take any, but you fix it that symmetric P and skew Q. Now you have to prove that A plus A transpose is symmetric matrix and A minus A transpose is skew symmetric matrix. So I have let it A plus A transpose as P. So what is A? It is given 1 5 6 7 A transpose. You can find the transpose of this, add to this. So this is the matrix P. Now you have to prove that this is a symmetric. To find the transpose of this 2 11 11 14, which is the same as P, so it is a symmetric matrix. Now I've let it A minus A transpose. You have to prove that it is Q, that is a skew symmetric matrix. So A minus A transpose, A minus A transpose. Transpose of A is this, subtract it, 0 minus 1 1 0. Find the transpose of it. It will be 0 minus 1 1 0. Take minus common in it, and it is coming out to be Q, that is minus Q. So Q, which is equal to A minus A transpose, is a skew symmetric matrix. So A plus A is always symmetric and A minus A is always skew symmetric. You learn it. Now in question number 9, again the same thing is there. You have to prove that half A plus A transpose is symmetric and half A minus A transpose is skew symmetric. The matrix A is given as 0AB minus A 0C minus B minus C 0, and the transpose of this matrix is this. Add these two, which is coming out to be null matrix, and if we find the transpose of this null matrix, it will be a null matrix, that is, it will be equal to P, so it means it is a symmetric matrix. Now half A minus A transpose, the matrix transpose matrix A is given, the transpose of this A is this. Subtract these two matrices, you are getting this. Take multiply this matrix by 2, you are getting 0 A B minus A 0 C B C 0 minus B C 0. Find the transpose of this, 0 A B minus A 0 C, like this. You know how to find the transpose. Take minus common in this, it comes out to be a Q, which will be equal to Q, that is minus Q. So it means a skew symmetric means you find the transpose, take minus common, and it will become negative of the original matrix. So it will be a skew symmetric matrix. Now in question number 10, you have to break a given matrix in which one is a symmetric matrix and another is a skew symmetric matrix, and you have to prove that after breaking the matrices, you have to prove that the individual is symmetric as well as skew symmetric. So let this matrix A as 3 5 1 minus 1. You have to break this into two matrices in which one is symmetric and another is is Q symmetric. So I have let P is equal to half A plus A transpose. You know that half A plus A transpose is always symmetric. So replace the value of A as 3, 5, 1 minus 5 A transpose. You know how to find the A transpose. Add these two, divided by 2, and find the transpose of this 3, 3, 3 minus 1, which is coming out to be P. That is, it is a symmetric matrix. That is 3, 3, 3 minus 1, which is a part of this matrix, is a symmetric matrix. Now you let half A minus A transpose is Q, replace the value of A as this. We have let it equal to A minus A transpose, subtract it, divided by 2, find the transpose of this, which is 0, 2 minus 2, 0, take minus common in it. So 0 minus 2, 2, minus 2, 0 will be there, that it is equal to minus Q. That is this A half A minus A transpose, which is coming out to be 0, 2 minus 2, 0 is a skew symmetric matrix. So we have break this matrix into this plus this, and we have proved that these two, this is symmetric and this is skew symmetric. We have just proved it. So this is equal to this plus this matrix. If you add these two, it will be equal to this, in which this is symmetric and this is skew symmetric matrix. And there are many parts in this question number 10. In all the part you have to prove it like same. You have to do it just as we have done this. In all the part you have to do this, rather it is whether it is a 2 by 2 matrix or a 3 by 3 matrix, you have to do like this. In question number 10 you can do all the question like this. You let the given matrix as symmetric given matrix half A plus, let it equal to A, break it first as half A plus A transpose, let other as half A minus A transpose, let one as P, another as Q, and prove P as a symmetric and Q as Q symmetric. And in the end you have to like this, A is equal to P plus Q, the P is this, Q is this, in all the parts of this question number 10. Now in question number 11, it is given that matrices A and B are both symmetric, and you have to prove that AB minus BA is skew symmetric matrix. It is given that A transpose A, it is given that A and B both are symmetric matrices, and you have to prove that AB minus BA is equal to a skew symmetric matrix. So let it equal to Q, AB minus BA, taking the transpose on both sides, AB minus BA whole transpose, so AB transpose minus BA whole transpose. Now you know the reversal law. It will be B transpose, A transpose, A transpose, B transpose. B transpose is equal to B, it is given. A transpose is equal to A, it is given. A transpose A is equal to given. B transpose equal to B is given. Take minus common in it. It will be plus, it will be minus, and it is equal to Q, which is minus Q. So it means AB minus BA, which is equal to Q, coming out to be Q transpose is equal to coming out to be minus Q. So it means AB minus BA is a skew symmetric matrix. Now in question number 12, it is given that A plus A transpose equal to I. It is given, and you have to find the angle alpha. Now the matrix A is given, the A transpose you can easily find it. Add these two, to cos alpha, 2 cos alpha, minus sin alpha plus sin alpha 0, sin alpha minus sin alpha 0, cos alpha plus cos alpha 2 cos alpha. So 2 cos alpha is equal to 1 and cos alpha is equal to half. The cos alpha half will be when alpha is equal to 60 degree. So this is the value of alpha in this question. Now after that we have a very important topic of invertible matrices. Now what is the invertible matrix? The two, if we have two matrices, let us say A and B, and if the product of these two matrices is coming out to be identity matrix, let if A into B is equal to B into A coming out to be I, then we can say that A inverse is equal to B or B inverse is equal to A. This is a sign for inverse. If the product of the two matrices and is commutative and both are coming and their product is coming out to be identity matrix, then we say that one of the matrix is inverse of the another. So if AB is equal to B and it is coming out to be I, then we can say that either A is the inverse of B or B is the inverse of A. Now we can find the inverse of the matrix A by two method, which is first method is elementary row or column transformation method, and another is by using the formula which we'll do in the next chapter, that is in determinants. A inverse equal to 1 upon determinant of A into adjoint of A. We'll discuss this in the next chapter. Now in this next exercise we'll discuss the elementary transformation method to find the inverse of a matrix. Now there are some properties to solve this elementary row transformation method to find the inverse. The first property is that if we interchange any two row or a column of a given matrix in the left hand side as well as the right hand side, and how can we write row 1 interchange with row 3? So our first and third row you can interchange. First row will come third and third row will come first. This is known as the interchanging the rows into column and column into rows. Now the second property is this, that we can multiply any row or a column by a given non-zero real number. Suppose we have matrix A is this 1 2 4 5 and R2 is equal to half R2. That is, we are multiplying the second row by half, our non-zero real number. So we can multiply, but you have to multiply both sides. We have multiplied the second row by half, That is, we can multiply any row or column by non-zero real number. And the next and important property is the addition to the element of any row or column, the corresponding element of any row or column multiplied by any non-zero number. That is, to any row or column, see, listen very carefully, to any row or column, a multiple of any other row or a column with a non-zero real numbers can be added or subtracted. If you take this matrix A as 2, 3, 4, 5, I can write as the matrix A row R to row 1, you can add the twice of row 2. To any row or column, the scalar multiple of any other row or column can be added or subtracted. So what I have done in this, I multiply the second row with 2 and add it to 1. This is a very important property and we have to use this property in almost every step. To any row or column, a scalar multiple of any other row or column can be added or subtracted. In this example, I multiply the second row by 2 and add it to 1. So it will become, multiply this by 2, it will become 8 and 10. And if I add 2 to 8, it will become 10. If I add 10 to 3, it will become 13. Similarly, we can subtract like this. To any non-zero number, multiply to any row or column and add it to the another row or column. This is the property we have to use. So these are the three main properties which will be used in the next exercise to find the inverse of a matrix by elementary row or column transformation method.